So you guys are going to be using a program what's called Tracker Video Analysis Software, if I even said it right. I call it Tracker for short. So it's a program that's going to allow us to track an object that's in a video. So all the videos have been set up for you. But when it comes to your project, a lot of people last semester, in fact, everyone last semester used this program. And so a lot of you may do the same thing to track an object in motion and analyze it for your project. We need to run the program off of a memory stick. I tried to have it installed in computers. It installed in some, not in others. Ultimately, it was easier to just purchase little memory sticks. So the program's installed here. So there's enough for one for each of you. You go to Computer Lab, you put it in, you let the computer magic happen, and a little box should appear like this. So it'll ask you what you want to do with this memory stick you just put in there. You want to open the folder to see it. And there's a few different things in here. Top one says course files. If there's any digital files of the course that you want, you can nab them. Handbook, problem sets are there. There's some other simulations, this FET stuff. We've used it before. We'll get to that right now. So there's tracker video files here and a tracker folder there. The video files contain just that. The videos, and I clicked on one. The videos that we're going to be using throughout the course or throughout this assignment next few days. So the first place you're going to go through is this tracker folder. Now you see a lot of different things here. What we want to do is just execute the program. I can't make a shortcut because every time you put that memory stick into a computer, it might assign it a different letter. My computer assigned it an X up there. The computer lab might assign it E or F or G, so I don't know. So this is the easiest way to do it for sure. And just double click the execution file. It's got the little symbol on it for the program. Don't uninstall it. Make sure you run it. So double click it. It should start up. It's running from the memory stick. It worked well last semester. Hopefully there's been no security changes to counteract that. So you see a blank screen with a bunch of different frames on it. The big one is where your video is going to go in here. Over here is where your data is going to be plotted as you're making it. And below is your table of values. So if you want to not see or zoom in, you can change all of this to the view that you like. You want a bigger graph, maybe you don't really need to see a table of values, you just want your graph, you can do all of that. I wanted that to come back. There we go. Okay. So these steps are in a file that on a sheet of paper that I'll hand out. I didn't print out enough of them, okay, but I'll give it to you for tomorrow. It's just a quick start guide. The electronic version is on my teacher page. All the video files that we're using right now are on my teacher page if you happen to not have them on the memory stick. So what I have to do is load up this file. Well, the file is, the video we want to use is on the memory stick. Problem is, if we run the video off the memory stick, the program is going to always try to find that video on the memory stick. And if you end up using a different memory stick, it might use a different letter. So the safest thing to do is to copy the video that we're going to use from that memory stick onto your hard drive. So first video we're using for the next couple of days is this one here called cart collision mass difference. And you're just literally going to, on your computer, just drag it and copy it into your file. I want to copy that. It's not letting me just right click. Do it this way. Copy that, and then for me, I'm going to put it on my desktop. But for you guys, put it directly into your folder. You know, I'll do the same thing. I'll put it right into my folder. There. It's not too big, 12 megabytes. Okay. So I went right into where all of my stuff is saved on the network. Don't save anything directly to a computer here. It gets deleted when you reset the computer. Okay. You might see it on the desktop. Next time you load it up, it's gone. So don't do anything like that. So I'm gonna load up the program, load up the video. There we go. So you open, and it's looking for either video file or a tracker file. So let's see. I've got to make sure I get to my folder. I don't usually run stuff off of here. There it is, cart collision mass difference, open. It's going to load the video up. A video of two little physics carts that are going to collide together and they'll bounce off of each other. It was recorded with kind of lower resolution, but it's slow motion. It's not the new slow motion camera we have, it's the one from before that. You can play the video as soon as you load it up. Now, a good chunk of this video is nothing because recorded a while ago, I had to hit play on the camera, get around to either end of this track, push these two carts together. Didn't take very long in real life, but when you're recording at 8 times slower speed, it drags on for a bit. So you can fast forward that. There's, oops, fast forward too far. Okay. Prepare to fast forward. There they come. Just two cars, they're going to come towards each other in slow motion. The nice thing about slow motion is it may not be high resolution, but each frame, here I'm just going frame per frame, is fairly sharp. Now the resolution is a little bit lower. Some of the videos we have will be high resolution, but they're sharp. You could take an HD camera, record this, and it's just going to be blurry. It might look good. It'll be HD when you play it at regular normal speeds, but when you try to analyze it frame by frame, it's going to be blurry. Normal cameras, including your smartphones, tablets, all that stuff, under normal settings are recording 30 pictures every single second. Then when you play them back, it plays back 30 pictures every second in front of our eye. Same thing at the theater. It happens so fast it looks like regular motion. Well, for this camera, the setting was 240 pictures every second. That's 8 times more pictures. But when we play it back, we still play it back at 30. So it looks 8 times slower. You're seeing 8 times more images happening. So it looks just looks a little bit slower. Okay, stop that. What we need to do, stop it, is follow the instruction on the sheet of paper I gave you. There's 3 things we have to set up for this to even work. Can't analyze anything unless we tell the computer program what the settings were when we recorded this. If there's a little film strip up near the top left, close to the K underneath the track. You click that. You're going to see this image on your sheet. Make the numbers in that program the same as what's on the sheet. So the first one is 474. We're just not going to analyze all that stuff where nothing is happening. Just getting to the good part. Step size is how many data points you want, really. So step size will skip frames. This was recorded 240 pictures every single second. We don't have to analyze 1,000 images to get decent data. So we'll make the step size 5, and we're just going to analyze every 5th picture. End frame, we don't need to go right to the end of this video, 814. Start time stays at 0. Notice the frame rate by default is 29.97, so the normal kind of 30 frames per second. This camera was 240. Now this is crucial because that's how this program calculates time. It knows there's 240 pictures every second. So that means between each picture, there's 0.00417 seconds. So when we track the object when we track this object moving, we know that between picture to picture, that time was 0.00417. And once we know the distance, we can start calculating everything else. We know how far it moved. Next, we need a coordinate system. That's the purple axis. As soon as you click on that, it just defaults and puts it right in the middle. Just to make our numbers positive, we're going to move that by clicking on the origin, just moving it to the left, somewhere along the track. It doesn't have to be right up on the track. It's very important that this video is filmed straight on. If it was filmed at too much of an angle, we wouldn't be getting all the same results. It wouldn't be very accurate. Coordinate system's easy. You can put it, really, it doesn't matter where you put it, but we'll just, so that everyone has a similar analysis, we put it over there. The next and the last thing we put in there is this calibration stick. It's the right underneath the word coordinate. Again, if we didn't have 2 storm days, you would be following along on a computer at the same time, so it might be a little easier to do. This tells the computer program the distance between these two cross marks at the end, there and there. And I didn't want that. Reset that to 0. That's essentially a scale. Right? It's a sense of scale. So right now it defaults as 100. 100 what? It doesn't matter. If we measured this to here to be 100 centimeters, and that means this would be 1 meter, all of our data would be in centimeters per second. Well, we don't know that. So what I do know, and that's what the ruler's there for, is the distance between these two openings is roughly 20 centimeters, or it is 20 centimeters. So from there to there, that length isn't 100. Put it in as meters, 0.2. Okay. So now every piece of information we have that's a length will be in meters. The time is always in seconds. Okay. So now we're ready to start our tracking process. 3 important things to set up. Coordinate system, so we know where we're measuring all of our values from. So everything is going to be measured from here. It's just going to be a grid. You can see it on the screen down here near the bottom. Right? X equals 0.15, Y equals negative 0.03. X equals 0.17, Y equals 0.06. Remember, this is centimeters, or excuse me, meters. Above, this is how high it is above that purple line. Okay. We have our sense of scale. We've got a coordinate system. The clip settings are in, so everything is ready to go. So we create, also all those 4 buttons we use are right there in the middle. And I have to use my mouse. Create a point mass. Don't need anything crazy. It just means we're going to be clicking on a point, and I'm going to rename it. I'm going to do the blue car. You guys are going to do the red car tomorrow. You know what? I'll make the colors blue too. Color in blue. So you're going to see his points appear on the screen. They'll be blue, and over here they'll be blue when they track. So I'm ready to start tracking my object. I hold down the shift button. My cursor turns into a little target. So shift button turns into a little target. And you can just hold that button down the entire time. You don't have to release it every time. I hold it down and I click on the vehicle. And it's important that you try to click on the same part of the object every single frame. And it's going to automatically move forward by 5 images. So this part will get boring, but it's collecting like 100 data points very quickly. You can see it jumps forward. So I'm just trying to hit the same point on the car as it moves. This is every 5th frame. So if you're watching this on YouTube, you can like fast forward through all this part. It's not very interesting. I should have aimed for the tire, but I didn't see it at first. So this will be a little bit off. That's all right. But even now, it's already starting to look fairly linear. A couple of spots where I did not do a very good job tracking. It will be easier to track the red car. Oh yeah. Almost done. All over the place. That's all right. When you do the red car, you'll see a tire, or you see the front of the car really easy. And you can tell the angle is starting to come into effect. I can't see as much of the front of that car anymore. So a little bit of educating, yes. And there's the collision. The blue car just comes to a stop. That's good. And the red car keeps going. So tomorrow when you're doing the red car, you keep going all the way until the end so you have good data. So the blue car moved to the left, right? That's why it's, so the distance or its position from the coordinate system is decreasing every single frame. Nice negative slope, right? Nice negative downward slope. Everything's in blue. So there's our graph. If you click on the axis titles, you're going to see a whole pile of things appear. Most of it we don't need. Okay? We use a little bit more of it in grade 12. But see, I just changed it to Y. Y is measuring how my points, where my points were vertically, just like in your Y-axis. X is measuring where my points were horizontally. So that's what we're analyzing here, the horizontal motion of this car, just along that track, back and forth. If you want to take a look at the velocity spread, you can just do Vx. That'll tell you its velocity. Now, it looks messy, but the data points are varying from like negative 0.26 to negative 0.10, but they seem to kind of be cut right in the middle through the horizontal line, meaning constant velocity. This is data. This is what data looks like. We're going to analyze X. We're going to do that. Because looking at X, I've got a nice straight line, definitely linear relationship. And then after the collision, a nice horizontal line. So that is a velocity of 0. Horizontal line, the position is not changing. You can see that in the video. Right? So you can go back and forth between the video and your graph, help refresh some stuff from what we were doing earlier. Okay, almost done. We've got our data. We need to analyze it. Okay. Now on your sheet of paper, this is number 7. Use a line of best fit of your data to figure out how fast it was moving. To analyze it, we need to kind of enter a new screen into a little statistics screen. Right click on the graph and you get some options. Down there near the bottom, with a third from the bottom, is the word analyze. It's going to bring up a new interface. Data on the right and your graph on the left. So if you want to get any images of this, that can be done under edit. There's copy. You can copy the image, you can copy the data, right? It's all there. Because you will need to kind of put this into a Microsoft Word document so that you can email me it and I can check it and make sure you're doing it. Right, so there's our X versus time. Remember, X is just, it's like in math, X and Y are just general variables. X is horizontal position for us, right? It's where this thing was horizontally, T for time. We need to analyze this a little bit further. So I click on Analyze again. There's statistics, curve fits, and this thing called Fourier spectrum. We'll never use this, the bottom one. The top one will just give you more statistics over on the right with your table. We don't really need that either, because it's going to give you statistics for all of your data. We don't want that. We want curve fit, middle one. First thing it tries to do, and this is why we reviewed fitting, looking at data to begin with. The first thing it tries to do is take all of your data and fit it to a straight linear relationship. That doesn't make any sense because this object's motion changed. There was a collision and then the blue car stopped moving. So we don't want to do the line of best fit for all of the data. We want to do a line of best fit just for that first nearly 0.8 seconds, 0.85 seconds. So we're going to stop analyzing this line of best fit once it gets horizontal. And you literally just select the data you want. So I go to my table, and I select only the data. You should see all the points moving yellow. The line wiggles around a bit until it fits it. Oh, I went too far. It's okay. I just go backwards. I'll just do that last point there. So now only the data where the car is moving to the left, it's being fit. Down here in the bottom left of the screen, it says fit name linear. It defaults to linear. If you happen to see a parabolic pattern with your numbers, you could do parabolic. That's obviously not a very good one to do. AT squared plus BT plus C should sound pretty familiar to you. Well, this is just X equals AT plus B. Putting that into a form you're used to, it's Y equals MX plus B. But Y was the vertical axis in your graph. Well, X is our vertical axis here. That seems a little bit different. X is not vertical axis anymore. X is horizontal position. It's position of this object along the x-axis, like horizontally. So it's horizontal position versus time. So X equals AT plus B. If you remember your math a little bit, the number that multiplies the variable, that's your slope. That's your average velocity. So parameter A directly across, there it is there. Negative 1.842 E minus 1. This thing goes straight to scientific notation. Okay? So E minus 1 stands for times 10 to the negative 1, which means move your decimal place 1 to the left when you're going to write this down. This thing's average velocity was negative 0.18. So when you copy this into your table of data, don't put the E there. Remove the E. This is really negative, this is going to let me write, yep, 0.1842. It'll always have that E there because sometimes the numbers are really big or really small, and there's just not a lot of space. Parameter B, that's just the y-intercept. So that would be the starting position away from the coordinate, from the origin of the coordinate system up here. Questions? That's a lot to sink in, so I'm recording it. When you do yours on tomorrow on Friday, you're going to see two lines. The car is going to start moving to the right, which means your position's increasing from the origin. It's going to collide, and then if you remember that red car, it bounced and started moving to the left. You're going to see kind of this pattern. So you're going to see two linear relationships. One for moving to the right, one for moving to the left. You just analyze them both separately. It's really just an introduction to the program more than anything else. And we'll go into more depth with the program after March break when we come back and look at something that's accelerating, because acceleration has a nonlinear pattern to it. And done.